So yeah, my name is Alan Hainline, and I live here in the Dallas, Texas area. Married with 4 kids that are now adults in their 20s, and I've always been drawn to this argument. Well, for I guess probably since even the late 80s or so. I have a physics degree from UT Austin, and studied some at Biola University in the graduate program there in science and religion. Have a master's equivalent in software and science engineering. Recently taught at the college at Southwestern on some physics and philosophy related issues at the undergrad level, and have taught some for UT continuing engineering studies as well. And yeah, I'm very interested in kind of tracking this argument, and I think it does provide some evidence for God, as I'm going to make a case here.
My training is in astrophysics. I have been interested in science for as long as I can remember. My dad was a chemist, and I just really enjoyed his job. And so I've just been interested in science for as long as I can remember. I studied high energy astrophysics processes. So these are gamma rays and black holes and neutron stars and dark matter, kind of the high energy exotic stuff in the universe. That's kind of my scientific training.
Is the universe fine-tuned for life? That's a claim that's purely a scientific claim. And then we can look at what are candidate explanations. And I'll argue that certain ones that are commonly offered fail, and that the best candidates are either the multiverse or design. And that if it's design, I think there's a pretty good case that the designer would be God at this foundational level of setting up constants and initial conditions. So one thing I'd like to raise attention to, if you haven't heard, there's a really great book that just came out. At least I got my copy on Kindle this week, and it's by Cambridge University Press by 2 very prominent physicists. Luke Barnes is younger, so he maybe hasn't established his career for as long, but he's certainly, I think, probably the foremost expert in fine-tuning, having written the most extensive, comprehensive review of the literature on the fine-tuning argument. And he's partnered with a fellow University of Sydney professor there, Zweerink Lewis, who also, both of them have PhDs from Cambridge University. And Lewis argues in the book for multiverse as an explanation, and Barnes for theism. So it's a really great dialogue. You're getting a lot of great physics. It's geared towards the lay level, but there's a lot of depth there as well. But they do a good job of making it understandable. And I was actually one of the ones that took a look before the book came out and was very impressed then. And the final version, haven't worked my way through all of that, but it looks fantastic. And it's got a great recommendation by Brian Schmidt, who's a Nobel laureate. And so I think this is going to get a lot of attention. Even one like Tim Maudlin, who some of you might remember, he was arguing against fine-tuning at the conference they had in New Orleans as part of the team with Sean Carroll. And he wrote a really nice endorsement of the book as well.
So this evening or today or this morning or wherever you are in the world, we are blessed with the presence of a very prolific astrophysicist from University of Sydney by the name of Dr. Luke Barnes. Dr. Barnes is a recent author of the book A Fortunate Universe, Life in the Finely Tuned Cosmos. He is also the author of what is probably the most extensive literature review in the scientific literature on the fine-tuning of our universe. And so he's going to be exploring some of the implications of the fine-tuning of our universe for life of any form to exist anywhere at any time in our universe's history. So Dr. Barnes, do you want to maybe just, before we start, just introduce who you are for those that haven't come across you before, and then just to kick into your presentation? That would be awesome.
Yeah, so I'm an astronomer at the University of Sydney. I've been there since about 2011 as a postdoctoral researcher. So before that, I was a postdoctoral researcher at ETH in Zurich, Switzerland. And before that, I did my PhD in astrophysics and cosmology at the University of Cambridge. So I'm a native Australian, and I'm back in Australia, and It's 7 a.m. over here, so if anyone wants to know what Sunday is like, just ask, because I'm already there.
So basically, here's the thesis of my presentation, and I'm basing this on something that came out of a debate between atheist Peter Millikan and William Lane Craig a few years back, where Millikan said, I would concede that if there is an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities, that would make a complex universe possible, then this constitutes a phenomenon that very naturally invites explanation in terms of a cosmic scale designer. So I want to basically argue that we have everything that Millikan concedes here, so that we do have an argument essentially for God from this data. So a bit more background about fine-tuning. We can fly through this pretty quick because I think this is a pretty sophisticated audience, but some of you might recall the Arizona biosphere set up a number of years ago where they were trying to have self-sustaining life and set up something which, if it worked, they could in principle take it to another planet and have life inside of that. But it was very difficult, they found, to actually construct a self-containing area like that would be good for life. Okay, so that's really the kind of thing that we can apply to the universe. The whole universe can be seen as a biosphere. Is it something which permits life to exist? And this would be called then the fine-tuning of the cosmos.
Great. Do you want to just move into your presentation?
Excellent. All right, so let me give you a brief overview of the first sort of 5 or 6 chapters of Fortunate Universe, and what Geraint Lewis, who's a professor at the University of Sydney, and I discussed there. Why is gravity that strong? Why is electromagnetism that strong? Why does the universe contain this amount of matter? Why is it expanding at this rate? We would love to know those things because those represent sort of the edge of physics as we know it. And so one of the things that we can ask is, what if the universe were different? And this isn't just some, random sci-fi novel about how the universe could have turned out differently. We take the fundamental rules, the deepest laws we know of, and we can change them to see what would happen, just to see if we get any insight as to why these numbers have the values that they do. That's the first 6 chapters of the book there. There's some very entertaining ways if you want to know what would happen, or if you're some sort of supervillain who wants to ruin the universe, then there's some really great ideas there. So I should mention at this point, Geraint's a colleague of mine. He was my master's supervisor. He's a professor at the University of Sydney. He's also an atheist. So we wrote the first 7 chapters of this book together, and there weren't any sort of major disagreements. There's one, if you want to get a copy, there's one footnote you can go and find, which just says, at this point, there was a disagreement between our heroic authors. But other than that, the science is fairly well nailed down. There's new developments happening. It's an active area of research, but it's something where, a lot of the scientific literature is just there. It just says what would happen if these numbers were different. That's the sort of thing that theoretical physicists should be able to do. And there's not too much dissent about the sorts of things that I've been talking about thus far.
So Barnes, in his review article that I mentioned, he references 200 articles that affirm this claim. And I do want to give credit to Luke Barnes, because I think he is a very careful thinker on this. He's philosophically informed, and he's very knowledgeable. And so I want to credit him with, if you see a lot of things in this presentation would be based on his material. So give him credit where credit is due.
If string theory is correct, not much actually changes. Less changes than you think. So in physics as we know it, there's the equation, and there's numbers in that equation, like the mass of the electron. And then there's the way that the universe turns out to be, and then there's the numbers in there, like how fast is it accelerating and dark energy and all of that. So the constants and the initial conditions. If string theory is correct, there are no constants, basically, in the theory itself. But all that happened is all the constants that were in there, like the mass of the electron, just get pushed down a level into the initial conditions. They're a property of the way the universe actually is, rather than something in your laws. and fine tuning is exactly the same as it was before.
Well, I'm going to say I think it's actually
That's
stronger than that.
Okay.
That what is referred to as M theory isn't even a theory. Yes. It's a collection of ideas, hopes, aspirations.
Exactly.
It's not even a theory. And I think the book is a bit misleading in that respect. It gives you the impression that here is this new theory which is going to explain everything. It's nothing of the sort. It's not even a theory, and it certainly has no observational. It partly is this 10 to the.
All right, so we see there that there are at least some significant scientists, such as Penrose, that seem to be rather skeptical about the ability of skeptical about string theory in general. All right, here's an interesting quote from Stanford physicist Leonard Susskind, where he says, "Science may be undergoing a huge course correction. A titanic controversy has erupted over the pattern of extraordinary unexplained coincidences that are necessary for our own existence." So I did a query. This was a little bit dated now, but it was still, even if the trend didn't hold up, I think rather interesting to look at the number of articles referencing the term anthropic, which anthropic means supporting man, or really mostly what they mean is that supporting observers more generally. But you can see that it is something which is talked about vastly more than it used to be within the peer-reviewed physics literature. So the first question you want to ask, though, if you want to say there's fine-tuning, is, well, is there a wide range of possible physics? And I think here that it's very much in consensus that physicists think the constants could have been different. Nearly all major physics departments are heavily invested in theories that entail constants could have been different, things like string theory especially. And that there seem to be certain parameters, such as spontaneous, the weak angle is thought to have, its value is thought to have been taken on by sort of a random process in the early universe, which is due to spontaneous symmetry breaking. In other words, just like a pencil on its end, would be very unstable and tend to fall in a direction, but it might be very hard to predict which direction. It might be kind of a random thing. Similarly, at least with one or two constants, I think we've already shown that they seem to have an environmental aspect to them. All right, so there does seem to be nothing in our physical theory that dictates initial conditions in particular. So far, the standard model doesn't give you a reason for specifying exactly what the mass of certain particles would be or things like that. There might be a deeper theory that constrains them somewhat, but deeper theories like string theory open up, I think, a wide variety of possibilities. And certainly with respect to initial conditions, there doesn't seem to be anything that would dictate how those would be set. So we'll kind of fly through some examples of fine-tuning here. There are 4 fundamental forces of nature, and you do have to get them in the right balance to have life. Matter density, energy density, number of dimensions of space. Even it turns out life is only possible in 3-dimensional space, according to many physicists. And things like dark energy and dark matter. I'd also like to argue that it's not as though our fine-tuning claims are going away over time. I think that it's held up quite well to a lot of scrutiny since it was first discovered in about the late 70s or so. And we are, I think, discovering some new fine-tuning over time. There was an article recently, it was not too long ago anyway, 5 years or so ago, they did some analysis it's been known for a long time that water has exceptional life-giving properties that are very kind of unusual. That's vastly different than other liquids. And the fact that ice floats, that evaporative cooling works so well for organisms to cool themselves, that capillary action works as well as it does because of the viscosity of water. All these different features we've known about for a long time, but it's now understood that if the way that quantum effects had not canceled nearly exactly, we would have ended up not having those life-giving properties. There's this incredible delicate balance. And so, yeah, it's another example of fine-tuning as to why it produces those effects. All right, so yeah, there's a lot more that could be said about water that we don't have time for, but it actually does come into play even in the hydrogen bonding and DNA, different things as well. It turns out that we're discovering that the ratio of dark matter to normal or baryonic matter turns out to also require some level of fine-tuning. It may not be as fine-tuned.
Jason McCool asks, hey Alan, have you looked at the effect of tectonic activity on life? I've been hearing more cases of astrobiologists concluding that an extrasolar planet could not support life unless it also had seismic activity. So it seems like this adds yet another constraint on life in the universe.
Yeah, that's something that you do find a number of people talking about, the tectonic activity enabling recycling of nutrients kinds of things, and planets which allow for tectonic activity would seem to be more likely to be able to support a long-lived magnetic field. So yeah, it's difficult, I think, to apply that necessarily to the kind of fine-tuning I'm making in this argument, though, but it may well impose some additional constraints, but I don't know how you would really work that back to the fundamental constants. So here I am taking a fairly narrow view of fine-tuning and just arguing in terms of at the very most foundational level of physics that you could evaluate in terms of the fundamental parameters and the initial conditions. How sensitive are those to permitting life? So in summary, many cases of fine-tuning are to a mind-boggling precision, and it's in terms of the initial conditions, the constants, and it's definitely seems to be the case in my research, the very few physicists who have really studied it. I've met some who haven't studied it, who doubt it, but of the ones that are really have studied, read many of the peer-reviewed articles, etc., they seem to be quite in agreement with the data itself. Now, that obviously the interpretation, people are going to come down on different sides on that. Now, there was, of course, the well-known skeptic Vic Stinger, who wrote the book which I bought called The Fallacy of Fine-Tuning. But I really do think that Luke Barnes' peer-reviewed article was an excellent refutation of that. And that if you look at the interaction that Stinger and Barnes had online, it's accessible. You don't see Stinger really responding when Barnes says, for example, that 6 out of 8 equations in his Monkey God program were simply incorrect. You don't see Stinger trying to argue against the fundamental claims that Barnes was making. And so I think even if you don't know that much physics, someone could easily see that it seems like Barnes really won that argument. But I encourage you to look at it yourself. If you think Stinger had some strong arguments, look at Barnes' peer-reviewed article, look at some of their interchange online, and make your own decision. So often the other thing that I find striking is that there are multiple life-permitting constraints that have to be satisfied for a given finely tuned parameter. So if these life-permitting ranges were sort of chosen at random as to where they would even lie, what are the odds that they would overlap at all? I think that's a challenge to the multiverse, as we can discuss later. So I think my thesis that I put up at the beginning, we haven't fully reached there, but I think I've established some parts of this, or at least argued for them, that there is here again was Millikan's challenge to Craig. He said that he would admit that there's a good argument for God if there's an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities that would make a complex universe possible. Now, I would admit at this point, we haven't done anything towards showing that it's an inexplicable coincidence, and that's the focus of the next part of the presentation. People might also say, well, okay, improbable events happen all the time. Why is this something that's crying out for an explanation? And they would say that someone has to win the lottery, which really, depending on the lottery, is often not the case. But for fine-tuning, it's more akin to the comparison of the same person winning many, many lotteries in a row by buying one ticket each time. At some point, you might suspect cheating in that scenario. All right. Now, we're going to talk later about the multiverse. Sure, if you have enough tickets, somebody's going to win in all probability. And that's where the multiverse comes into play as a possible solution. But there you're multiplying your probabilistic universe, your resources. I think it can be helpful to consider the fine-tuning first from the standpoint of, let's assume there's just one universe. And I think there you do clearly end up with significant problems for these explanations. And then you can ask, well, what happens if we think there are multiple universes, and how do we weigh the pros and cons in that realm? And the other thing, when people say this, they seem to forget that, well, many times scientists do draw conclusions from improbable events. Namely, Bayes' theorem or Bayes' probability. And it can tell us whether certain data support a hypothesis or not. You can make relative comparisons. And so what I'm trying to argue in this is that naturalism is extremely unlikely to have produced life-permitting universes. I think the physics bears that out, with the possible exception of the multiverse, which we can discuss later. But I think certainly if there's no multiverse, that statement seems fairly non-controversial. All right, I've already talked about Stinger, but yeah, he was one of the few physicists to question fine-tuning itself. Really, Barnes in his peer-reviewed article, he's basically dissing Stinger's book. And I think he makes some very powerful cases that much of the physics was wrong, some of the philosophy, even challenges that Stinger really understood fine-tuning and what it meant in terms of the kind of argument that Barnes has anyway. And he drew a lot of conclusions from his Monkey God program where 6 of the 8 equations were wrong. He left out this epsilon fine-tuning factor, one of Martin Rees's 6 numbers. And he only considered one life-permitting criteria, whereas really you need to consider multiple life-permitting criteria. So I think that fails. There's really no silver bullet physicists out there that has shown that the physics itself is wrong. Most people that study it seem to agree that yeah, there's something significant going on here. But you know, at the lay level, sometimes people will say, well, you know, evolution will find a way, or they'll say, well, you're just being too narrow-minded about life forms. There could be other life forms where it's far easier to be life-supporting. But here's Lightman of MIT saying that if these fundamental parameters were much different from what they are, it's not only human beings that would not exist, but no life of any kind. It is true that some of the finely tuned parameters, it's a little bit debatable. Is it a strict limit against any kind of life? And that's where maybe adding the adjective intelligent life pushes it more in the direction of, well, it'd be really hard to get intelligent life in such a universe. But there's enough of these very clear-cut cases, like the cosmological constant. If that was very much bigger, the universe would have just been blown apart such that there would be a very low density and it wouldn't have had time to fuse together hydrogen into helium, etc. And thus you wouldn't have chemistry, you wouldn't have information storage. How can you do information replication if particles only bounce into each other every trillion years or so? So there's some catastrophes out there. I already mentioned this quote by Hogan. I mean, these physicists writing the articles, they seem to be, I think, pointing out some very severe issues that would prohibit life. They're assuming evolution can do quite a bit. The question is not what can evolution do once life starts, but can you get life to begin with at all? Barnes has done some good discussion of consideration of the best alternative candidate to carbon, namely silicon. But as most chemists will point out, silicon seems to be in every way less helpful than carbon for the kinds of things that life needs. Long chain molecules are less stable. If you oxidize silicon, you get something, silica, which is a solid, not a gas, which organisms could easily exhale, basically. And the more important thing to consider is that because silicon, it's a higher, basically the way you make these elements, and only a few came out of the Big Bang, the real low numbers, most of them are made in stars, but you're just slamming together these atoms and forming, you're fusing them together. Well, you have to make carbon on the way to making silicon. And so universes where silicon is abundant would also have carbon. So it really is not adding much in the way of giving you additional ways in which you could support life just by saying, okay, yeah, life could have been silicon-based. And the other thing to note is that most of these life-permitting things that we've been discussing don't say anything about the form of life. It's only the Hoyle formation of carbon and oxygen in stars that really relates to that. But it could have been the case without certain nuclear resonance levels that you would have had a bottleneck that prevented anything above carbon from forming. So that would have also prevented silicon.
See, there's as often when I bring up the fine-tuning argument, some of the atheists I interact with come up with some quite lame or superficial objections. One of those objections is, well, isn't any set of physical constants and parameters just as likely as any other. Do you want to speak to that briefly, Luke?
Yeah. One of the things you got to do with any objection is just try and apply it more generally and see what happens, right? Just to see whether you're being consistent. So you're in a courtroom, you're trying to, defend your client, and they've got the DNA evidence there, and they say, look, it's very unlikely the probability of this bit of blood is not your client's blood. It's very small because of DNA. And you say, yes, but any DNA strand would be unlikely. That doesn't help, right? I mean, the problem with this objection is that it's saying it's comparing two values of the laws with the assumption that, of the constant, with the assumption that they're just chosen at random. That's precisely the assumption we want to know. It's precisely assuming the thing we want to know from the start. Is it random, right? So, a poker game, and whenever I deal, I get a just sort of average middling hand, but I'm playing with Bob, and whenever Bob deals, he managed to deal himself a royal flush, right? If Bob says, look, the probability of a royal flush is the same as the probability of the hands you have, right? That's assuming that he's dealing fairly, which is the whole point of your questioning his whether he's cheating or not to start with. So the objection assumes the very thing that we're trying to question. The question is not whether this set of laws is as likely as that set of laws. It's whether this set of laws gives us a reason for thinking that there's some deeper reason for those laws.
You might struggle to put your finger on, well, what really did go wrong? But if you think about the assumption inherent in this claim, the poker hand being just as unlikely as any other, well, that's something that would not be the case, for example, if the constants of the universe were intentionally selected. Then it would not be the case that any set is just as likely as any other. So on naturalism, I would agree that any set of constants is just as likely as any other, but the right question would be, if the dealer dealt 10 straight royal flushes in a row, what's the probability she's dealing fairly? What's the probability that these were set at random, that the cards were really shuffled and dealt at random? I think we would recognize that the probability is pretty low that they were dealt at random if you got that many in a row. Another important consideration is the effect of what I would call the anthropic principle. Okay, so many would say, which is right, and it's something that needs to be accounted for, we can only observe that we're in a life-permitting universe. Elliot Sober put this quite well in an objection. What would you think the person that walked around saying there are no square circles, that it's impossible? And so why are we surprised about fine-tuning when it's impossible to observe a universe which is not life-permitting? But I think that is mistaken. In the case of the square circle, that deals with what's logically possible. But here it's logically possible that there wouldn't have been a life-permitting universe, even though in that universe there would have been no one there to observe it. I think if you consider the example also, John Leslie came up with this example of the firing squad. Consider that you were put before a firing squad of highly trained marksmen at point-blank range, ready, aim, fire, boom, but they all miss. Would you infer there might be some deeper explanation, or would you say, well, if I wasn't alive, I wouldn't be here to observe it, so there's nothing to be surprised about? No, I think that would be surprising in that scenario. You're not surprised that you do not observe your dead, but you're rightly surprised that everyone missed. The unlikelihood of the situation demands an explanation. Philosopher John Hawthorne, he was a philosopher, the lead philosopher of metaphysics at Oxford University for about 10 years. And he used to be one that was not seeing the force of the fine-tuning argument, but has recently changed his view on that. He sees something pretty significant in fine-tuning now. He has some good observations where he talks about, he says that there are some things we can learn where we couldn't have learned the opposite. I couldn't have learned that I don't exist, okay? But he says it's awesome evidence that there is something rather than nothing, just from the fact that I exist. So you can have evidence for something, even if it was impossible to observe it otherwise. So I think that's a kind of a good, simple example that people can wrap their heads around. The fact that I couldn't have learned I didn't exist doesn't stop the fact that I exist being awesome evidence. Okay, he also talks about a firing squad, but a little different context, saying, what if there's 2 boxes of guns, one faulty and one not? You survive the firing squad. Wouldn't you take that as awesome evidence that they used the faulty guns? Even though it's true that if you hadn't survived the firing squad, you would not have been there to learn that you survived it, because you wouldn't have survived it. So you can still have evidence for something, even if there is sort of an anthropic selection effect. And that's what it's best to think of this as, is a selection effect. You're not getting a random sample of data. It's biased by certain things. And that's something that physicists are pretty used to dealing with, and I think they're accounting for it well in these arguments. I mean, in order for there to be this kind of selection effect, though, you need a population. And so you need something like the multiverse to give you these other chances at life. And I like the way Hawthorne summarizes this. He says the other thing about this objection is its irrelevance. We're not talking about the relevance that the universe is life permitting, but the evidential relevance that life permitting physics is rare. We could have learned this to be false. That's what's gotten everybody's attention. No one thought there was a fine-tuning argument until they realized how narrowly fine-tuned these different parameters are for life. All right, some question, well, how well can we assess an exact probability? We talked about that a little bit a while ago, but some more thoughts. Consider the question of, what if I played LeBron James in basketball, what are the odds I would win? It would be incredibly low. Maybe if he randomly died at that particular time, I would win, or got a really bad injury. He'd have to have a bad injury to even win in that scenario. But even though I couldn't quantify that, I could still reasonably conclude that it's unlikely. And we've got all these different parameters that seem to, on fairly conservative assumptions, seem to give us these incredible levels of improbability. We may not know the exact distribution function, and I think there's some pretty good arguments for just using the principle of indifference. If you don't have any particular reason to think otherwise, then just assume the different possible values are equally likely. And that's really where you get these kind of quoted probabilities. Aguirre and Barnes have argued that we can generally approximate probability by assuming a linear or power law distribution, and that there's some interesting quotes by Aguirre that Barnes quotes, and that they even interacted with live together at the Philosophy of Cosmology, where they argue that if there was something to explain this fine-tuning, it would require it being peaked in this very narrow range. And so you would still end up needing some finely tuned parameters to make it peak in that narrow range. And so I think it's really hard to explain away this data, given that there is a wide range of possibilities. All right, an important consideration too would be, is there an underlying law that explains fine tuning? So if all the constants and the initial conditions were driven to the values they have by a law, then out of necessity, they would have those values, and there's no sense in which you could say that they're finely tuned, that it's improbable. Okay, but I think there are some interesting considerations here that, let's say that was the case, you would still have an issue with the initial conditions, because as John Wheeler said, never has physics come up with a way to tell with what initial conditions the universe was started off. And nothing is physics clearer than what is not physics. I was able to have a class with Wheeler when I was at UT Austin, and he was a great guy to lecture. And he was the one that coined the term black hole and some other contributions that were pretty significant. But anyway, so would a theory of everything, you hear that thrown out a lot, would that result in one possible set of laws? Well, in the past, there was some optimism towards that through string theory, but now it's viewed more as, instead of a theory of everything, more like a theory of anything. So string theory seems to increase the number of possible values for constants. It seems to transfer them from, there might just be like maybe one string coupling constant or something like that, but the parameters do become environmental on string theory. Depending on how you compactify the 11 dimensions that you need for string theory, ends up resulting in different constants of physics. And so these things become more environmental parameters. And so it might help you in a multiverse scenario to give you an explanation of the fine tuning, but it certainly doesn't drive them to one possible set of laws. Paul Davies has a strong quote on this. He says he thinks it's demonstrably wrong. There's not a shred of evidence the universe is logically necessary. Indeed, as a theoretical physicist, I find it rather easy to imagine alternative universes that are logically consistent and therefore equal contenders for reality. If you go back to the time of Aristotle, that's when they thought that, oh, you can just sit in your room and think about how the universe should have been and figure it out. But the long history of science has shown that that's not the case. You have to go do experiments. There's no underlying law or principle that's driving everything to be a certain way within the universe. Really, most physicists would say no to this question of a theory of everything making the constants take on certain values. Frank Wilczek, Nobel Prize winner, says it's possible, but I think it really strains credulity. Carr and Rees point out more generally that even if all these anthropic coincidences could be explained, it would still be remarkable that the relationships dictated by physical theory happen also to be those propitious for life. You would still have these remarkable coincidences that would seem to need an explanation because there's no logical necessity in the values taking on these certain values that they do, the constants taking on the certain values. Just a couple of weeks ago, they had this large conference in Poland talking about varying constants and fundamental cosmology. The whole conference was devoted to people considering the fact that the constants could have been different. And so I hear this at the lay level a lot, but I think among physicists, there's so many ways to vary the constants if there are additional dimensions, if something even remotely close to string theory is true. There's many different ways that we could have variable constant. John Barrow has a good article on this that I could point people to if they're interested, where he gives like 5 reasons to think the constants could have been different.
So all of that's fairly widely agreed upon. The question is, what do we do with this thing? So let me run you through the 2 options that we discuss in chapter 8 of the book. So chapter 8 takes the form of a dialogue where we go back and forth and try to work out what happened. So what Geraint wants to do is have more cosmology. So there's this idea called the multiverse, which has turned up in comic books for whatever reason. I don't know why Batman is there, but Infinite Crisis, fight for the multiverse. So here's the idea. So we won the cosmic lottery, basically. How did all these different conditions, all these different numbers come to be just right for us? Well, there's lots of different universes, lots of different places in the universe, maybe, and they all got different values of these constants. Most of them are dead for the reasons we've just discussed, but every now and then someone gets the right combination, gets the right lottery ticket, and hey presto, here's life as we know it.
So if we can define now the universe we'll talk about it in terms of the observable universe, that's a well-defined quantity, then really all the multiverse is just anything beyond the observable universe. Now that could come up, and there's different types of realms you could see there. So our universe could be part of what's just more than what's out. I mean, there's just more stuff out there. So that's that would be part of the multiverse. Or more likely that when people are talking about the multiverse, they're talking about other universes or other realms where things just look different, where the speed of light is going to be different, or the expansion rate is different, or there's no weak nuclear force. So just moving beyond the observable universe, that's going to be more of the same space-time, matter, and energy as what we see here. But these other bubble universes would be things where the laws of physics might even look different or have a different manifestation. So this is what most people are talking about when they talk about the multiverse.
So the next part of the presentation, we're going to consider I think the most plausible explanations of the fine-tuning, namely either God or the universe. Not all physicists would say it comes down to those 2, but it seems to be a growing trend toward that, and many of the ones that seem to have studied it a lot and thought about it, even if they're skeptics like Lewis and Susskind, would say, yeah, there seems to be a need for a multiverse to explain this. if you're not going to have God as the explanation. Susskind says, in fact, that the stakes are to accept the string landscape. And he admits that it results in this kind of dilution of the scientific method because of the inherent difficulty of validating something like string theory or other universes. But he says to do otherwise would be to give up science altogether and accept intelligent design as the explanation for the choices of parameters of the standard model. So seems to have a strong bias against even considering intelligent design, but yeah, he seems to think that these other explanations fail significantly other than one of those two, and he obviously seems to reject the intelligent design option.
The short answer is, while there are quantum mechanical interpretations that allow for a multiverse, we have at this point really no way to test which interpretation of quantum mechanics is correct. And so any sort of quantum mechanical multiverse is really scientifically speculative in that the sense that we can't really test whether it's legitimate or the actual way to look at it or not.
So what you would need in order for the many worlds interpretation to explain fine tuning is some way in which the mass of the electron, for example, is just some way the universe turns out, and then you let all these other worlds be created via this mechanism's the wrong word, via the many worlds. So it's not automatic. You don't automatically get, even if you thought the many worlds interpretation was correct, you don't automatically get the kind of multiverse you would need to explain fine tuning, because it doesn't vary these parameters. Mm-hmm. They all stay in the law. They're all the same. It just changes the way the universe is. So you would have to take the many worlds interpretation and link it to some idea about how these parameters can change and some cosmological idea about how the universe works. So it might be a bit of the puzzle, but it's not the whole story.
But I think it does boil down to, as Bernard Carr said, if you don't want God, you better have a multiverse. And in this book, it seems that both the atheist author Lewis and Barnes seems to be a theist, because he's arguing for theism here, but they both seem to strongly agree that these other explanations are inadequate to explain the fine-tuning. And so they would want to opt for multiverse or God. And I think both of them see a little bit of force on each side, but they do seem to pretty strongly favor their particular interpretation, which makes it a great book, I think.
Now, one of the interesting things about the multiverse that I want to stress is that actually there's an interesting way in which it might be testable. So here's an example of how it might be testable. Now, my experience over the last couple of weeks, I've just been giving some talks around the US, is that this is the slide at which some people get lost. So you can do this, people get this, but you're going to have to pay attention, all right? Or if you don't, you can at least enjoy this picture of Fry from Futurama. This is called Revenge of the Boltzmann Brains. And what we want to do is just treat the multiverse like it's any other scientific theory. So what does it predict? Well, it predicts a population. It predicts a whole heap of universes, each with different properties. And like any population, we can ask what its demographics are. What are the different properties of the different universes? How often does a certain property turn up? So we could, in our minds, of course, it's all in theory, but we could take our clipboard and our pen and we could go around to all these universes and say, what are things like in here? Now, for most of these universes, for the reasons I've said, if you knock on the door, no one's going to answer. There'll be no life there because they're totally dead, okay? But if someone does answer, you can say, all right, what do you see in your universe around you? What's the mass of your electron? How much cosmological constant is there? How big is your universe? And in particular, we're trying to understand observations of our universe. And because we're doing cosmology, we can't pretend to be standing outside looking in. If you want to know what will a typical observer see, it's a question of you've got to make the observer first, because this is cosmology, and then ask what they will see. So one of the things we could ask the person we find is, how did you get here? What is the process by which your little corner of the universe arranged you into being an observer? And here's the interesting bit. Boltzmann had an idea. Ludwig Boltzmann, famous physicist from the 19th century, had this idea about why our universe has one of the properties it does, that there's lots of low entropy energy around. Basically, the universe is still winding down from a highly ordered state to a less ordered state. So the ice cubes in your cup melt. That's an example of an ordered state becoming a disordered state, or a low entropy system becoming a high entropy system, the other way around. His idea was maybe this was basically a multiverse. Maybe the universe as a whole is in a totally disordered state, but just by chance, fluctuations and just stuff coming together randomly will produce order. And that's why we see the order around us, because we couldn't live unless we had low entropy conditions around us. We need ordered energy to be able to do things. We couldn't just live in a state of perfect thermodynamic equilibrium, perfect disorder. Here's the problem with that idea, which was pointed out about 30 years later by Arthur Eddington, nearly 40 years later. We get our clipboard out and we go around in that universe and we say, how did you get here? And anytime we find someone, what's the process by which you got here? If you're relying on a random statistical fluctuation to make order, the easiest way for it to make an observer an example of order is just to make the observer, just have it fluctuate into existence. The rarest way to make that is to make a huge amount of order billions of years ago, right? And have it make galaxies and stars and supernovae and planets and smaller life forms and let them develop up into larger life forms, right? By that process. That's not the way to do it, because that's even rarer than just making the thing you want to start with. If you're requiring a miracle to make an observer, it'll just make an observer. It won't make all the paraphernalia around it like we see in our universe. So the most likely answer to the question, what kind of thing are you when you go around your universe, is I'm just a brain in surrounded by total thermal equilibrium, total chaos. Right? So the problem with that is it's wrong. This is not the brain in a vat, am I in the Matrix philosophical thought experiment? How do I know I'm not just a brain? This is just, you got a theory, makes a prediction. What kind of thing are you when I go around and ask in the universe? And Boltzmann's multiverse says that most people should answer, I'm just a brain in a vat. So the fact that we're not that kind of thing is then evidence against the theory. The theory leads us to expect something, and that expectation is wrong, and so the theory is probably false. So that's called the Boltzmann brain problem. It's a way in which the multiverse could actually be wrong.
Okay, so consider that John Page has written, for example, that if any vacuum which is capable of supporting observers eternally inflates, again, that's the most popular multiverse theory, such a vacuum produces an infinite number of Boltzmann brains. And a couple of other authors say that to exhibit a paradox in the global description of multiverse, the overwhelming majority of observers arise from quantum fluctuations and not by conventional evolution. So recall that I said this anthropic principle is a selection effect. You're selecting for observers. But if the observers are predicted to be different than what we find in our universe, not just a little different, but vastly different, then I don't think that would make that multiverse proposal not a good explanation for the fine-tuning of our universe. And I'll admit, there are ways around this. Sean Carroll's written some things, some ways around this, but the thing seems to be the case that you had this initial round of articles where people were on very general analysis saying that this is a natural byproduct of the theory of eternal inflation. But I think if you can tweak some parameters, if you can do some fine-tuning, basically, you can get around the Boltzmann brain problem. But again, the problem is if you have to do fine-tuning to avoid this problem, then have you really removed fine-tuning? I would argue not. Right.
No, that's very much the case. And Sean Carroll, who's done quite a bit of work and speaks fairly popularly on things, he argues that Boltzmann brains are, I think the term he uses is cognitively unstable, because you recognize that again, the probabilities are difficult to actually address, but in most scenarios, it seems like the Boltzmann brains are more likely than normal, ordinary observers like we would consider ourselves. Now, a Boltzmann brane, the most likely Boltzmann brane is not one that has this long history and everything's well ordered. It's a fluctuation where the history is imagined. And so if it's more likely we're a Boltzmann brane, then all the memories we have are really non-existent. That's the most likely scenario. And so we can't even trust our ideas about what's going on if we're a Boltzmann brane. But what I find interesting is his solution to that. So what he does is he looks at the different scenarios we have out there, and he applies a criteria that any universe that produces Boltzmann branes isn't a good model. Well, that's designing things. It's saying, all right, in this scenario, or of the possible outcomes, we're eliminating the ones where you got Boltzmann branes. Well, I could also go and say, in my models out here, I'm going to eliminate all the possibilities where carbon doesn't exist. That's how you end up with, that's how we ended up with some of our fine-tuning arguments for the laws of physics. Well, to me, it seems like all he's doing is just designing things so that we don't get those unworkable scenarios. But that's still design. Or that's fine-tuning, design, purpose, whatever you want to call it, it's still being applied there. So, as I've looked at this, a lot of times, we'd have this particular design argument or this particular argument for fine-tuning, and we'd kind of squeeze on that, and scientists might solve that, but that design ends up popping up somewhere else. It's hard to put that into an argument or quantify it or stuff, but it seems like that happens very regularly, and I can give you numerous examples where that's happened.
So it turns out that nearly all initial conditions of the Big Bang would have resulted in a lifeless black hole universe. Roger Penrose is, I think, the first one that computed these odds, but many other people have confirmed them. But he puts the odds against life at about 1 in 10 to the power of 10 to the 123rd. So not just 1 in 10 to the 123rd, but 1 in 10 to the power of 10 to the 123rd. So writing out that number in normal form, like if you just included all the zeros, you wouldn't have enough particles in the universe for every zero in that number. And he considers whether the multiverse might help with this, but he says that it's actually worse than useless in explaining the anthropic fine-tuning for this parameter anyway, because it predicts exponentially smaller universes. So multiverse predictions are so vastly different than what we find in our universe that he views that as reason to consider multiverse proposals and explaining this worse than useless.
Roger Penrose at Oxford University, according to him, the vast majority of arrangements of matter in our early universe result in universes dominated by black holes, and that's obviously not conducive to life. And according to his math, the ratio of life-favoring universes to life-disfavoring universes is 1 in 10 raised to the 10 raised to the 123rd power, which obviously has more zeros after the 1 than subatomic particles in the known universe. Do you think that's a strong argument as a case of fine-tuning?
So, yeah, the initial entropy of our universe, I think, is a particularly strong case. It's sort of dawning on me how much stronger it is than a lot of the other ones. The reason is that it's the one that really hits the Boltzmann brane problem hard. It got that was the sort of explanation of how do we get the low entropy, the order in our universe. You just wait around until it happens by accident. The problem is you'll only get as much as you need, and you're probably just a brane in a vat, right? That's a problem. That argument is basically the same as what it happened to Boltzmann. All that Penrose is doing is applying the same thing to the very earliest stage in our universe and an understanding of what the ultimate high entropy state of the universe would be, which is just totally filled with black holes. And you get the numbers you get out are ridiculous. They are extraordinary.
He actually was able to do some computations, and the way he did them, it related to using the equation for the entropy of a black hole, which then allowed him to draw some conclusions about how special that would have to be in terms of those initial conditions. So it's not necessarily to really understand how the Big Bang came about or what was the physics before Planck time. We don't really need to answer those questions as long as there's this understanding that the second law seems to apply, that you're going from lower entropy to higher entropy And it looks very surprising that our universe would have such low entropy that allows for things like stars, these long-lived energy sources, that you would have this much usable energy this late in the development of the universe. If you start looking at all possible ways of arranging particles, it becomes very surprising.
There's the what is required and what is extraordinary. And so, the minimum Boltzmann brane is just the one that pops into existence and recognizes it's there. If we're a Boltzmann brane and we're not one of those, we're really unusual. And so your statement is kind of along the lines of, the minimal universe that could support life would be what we would expect to be in. And the fact that we're in a pretty extravagant universe is against that.
Every explanation which is consistent with the second law of thermodynamics, which is all of them, you'd hope, starts with a highly ordered state. So the question of where did the order in our universe come from is not the sort of thing that science has ever explained. It's always been the starting point of every explanation. So if the order of the universe you see around you, the order of plants that you eat, and of everyday life impresses you, all of that just goes back to more and more and more and more order in the early universe. So that, I think, is a pretty interesting fine-tuning case. In that it's something that which looks in need of an explanation, but which scientific explanations have never touched.
So he finds it very surprising on multiverse theory, on general grounds, that you would have a life-permitting universe that would be of this large size. One way to think of it, and by the way, Sean Carroll's written on this too, and he also agrees that the multiverse and an anthropic multiverse explanation fails for the low entropy condition of the universe. And you can think of it by thinking in terms of what do we need for life? We certainly don't need anything more than our solar system. We could survive quite well with just the sun and the planets. Maybe you don't even need all the planets. It's a little bit debatable how much they might help or hurt on asteroids. But maybe if you had nothing else, maybe you don't even have to worry about incoming asteroids from other solar systems, etc. And then finally, one more thing that a multiverse must overcome if it's going to be an adequate explanation of fine-tuning is that it should not itself require fine-tuning, or that would just shift the problem up a level. I've already given an example of this in the previous discussion, but consider that even Sean Carroll says that the probability of inflation occurring in a universe where you have the initial conditions chosen at random is about 1 chance in 10 to the 66 millionth power. So that looks like a lot of fine-tuning to me. Now, there might be ways around this, but certainly if you just look at the history of inflation, there was a lot of ways in which the theory was originally described in ways that wouldn't work. So you can see that it requires fine-tuning just by looking at the history of inflation proposals. There was a graceful exit problem. It turns out it was hard to get inflation to stop. And if it never stopped, you certainly would never have life because you just have this runaway expansion.
I know some physicists have suggested that the multiverse itself would require a certain level of fine-tuning. Would you agree with that assessment?
Yes, I would, and it requires a level of technical detail that's difficult to get into. But what is true is that, so if you're talking about an inflationary multiverse, this mechanism where you've got this inflating space and bubble universes are produced, what often gets missed is that in order to get that inflation to work properly, the inflation potential has to be highly designed. If you look at just kind of generic potentials that would drive that, or to try and drive that, it won't actually drive inflation, or it won't produce the size of universe that we see. So even the inflationary mechanism seems to be fine-tuned. In fact, there is a fairly prominent cosmologist, Paul Steinhardt, who was working with, doing very, research into this area back in the 80s when it was, people were looking at inflation. And part of what convinced him that the inflationary mechanism isn't right is just how finely tuned it is to get it to work. So, I didn't really address that in here, but for even the inflationary mechanism requires quite a bit of fine-tuning.
John Rood submitted a question. He says, in order for there to be a multiverse, would there need to be a universe-creating mechanism? If so, could we theorize that a universe-creating mechanism also requires fine-tuning?
So I think the answer to that is yes. It's not that there has to be a mechanism. It's just if there's not a mechanism, then each individual multiverse in your each individual universe in your multiverse is a separate postulate in your theory, right? And another universe, and another universe, and then Occam's razor is going to kill it. Okay, if you have to make the sort of numbers you get out of fine tuning suggest that the number of universes you need in order for anyone to win the lottery is enormous. So if each one of those is a separate postulate, then you're in big trouble. So I think the only real viable multiverse candidates are the ones where there's a generator. So then the question is the generator itself fine-tuned? And the problem is we don't know because we don't really have a good theory. So one of the reasons we can do fine-tuning with the theories we have is because we have a solid theory. We know it explains our universe. As I explained that whole bit at the start about how we understand stuff in our universe, we can now go and do theoretical physics and change stuff. We just don't have that with the multiverse, so it's kind of unknown. I would expect, now, given what we know about how hard it is to make life, making a life-limiting multiverse might not be easy. So, for example, if it's based on inflation, if this idea about how the universe expands really fast in the earlier stages, if you want to use that to make a multiverse, you have to worry about the fine-tuning of inflation. And there are a lot of worries about the fine-tuning of inflation. You don't get that for free. You don't get the multiverse that comes out of that for free. So I think it's quite likely. The best handle we have on some physics we can actually change to see whether they are fine-tuned is the laws we have. We would try and do the same thing again if we thought there was a multiverse, but the problem is we're working in the dark a bit.
Lizzie asked a question. Can you give a simple analogy for the inflationary problem that means the multiverse requires fine-tuning? And so the example I would give is that the inflation is in a very high potential, and then when it comes down, it's going to go to a low potential. And so the example would be you put a ball on top of a hill. Ball rolls down the hill. That's just simple. There's nothing fancy about that. If I now need to get that ball into a hole that's up another hill, I have to design the hill so that the ball gets the right speed and it goes in the right path and ends up dropping in the hole. Inflation kind of has a potential like that. It's not just let's roll downhill. It's got to be the right kind of hill that doesn't go too fast. It doesn't slope too steeply. It doesn't steep or it's not too shallow. It comes out. It's got this. The low state is out around, not at the center. It's just a very weird looking hill, if you will. And so, hopefully that's a little bit helpful. But it's got to go from a high potential to a low potential. But it's not just let's roll downhill. It's got to roll downhill and hit a number of balls, and it can't go too fast and it can't go too slow. And then it's got to get up the other side and drop in the hole with just the right velocity. That's kind of an analogy of what you might have to do, except it's actually a lot more fine-tuned than that.
And it seems that if you have a universe generating mechanism, then it's very difficult to see how you could avoid that being finely tuned as well.
It is, I think. Yeah, I mean, that doesn't seem like the easiest kind of, if you were thinking of making a machine like that, it doesn't seem like the easiest kind of machine to make that would just crank out huge numbers of universes and so forth.
Especially with all the different combinations of constants and everything.
And one of the problems you have is that I think people are led towards these theories that produce huge numbers, because then the fine-tuning is not a problem. But it's almost like that's where you get into the Boltzmann brain type problems. If there's too many of these other universes, it tends to be really hard to end up predicting large, finely tuned universes as opposed to Boltzmann brains or smaller universes that don't require as much fine-tuning. All right, a fourth challenge for the multiverse is that, if a theory leads to absurdities, it gives us good reason for rejecting the theory. According to Zweerink, eternal inflation requires the Everett many-worlds interpretation of quantum mechanics. Now, that may or may not be true, but many physicists strongly reject this notion that every quantum event could lead to a parallel, or maybe a better term would be a perpendicular universe. And Zweerink points out that the ramifications of his multiverse theory actually result in there being regions in the multiverse where Al Gore is president, and yes, Elvis is still alive. So it's really funny seeing these kind of things in a peer-reviewed article.
Or more likely, another one is, we tend to think that we're an actual history of things. It's possible that, again, if life is purely physical, you can simulate universes. And there may be advanced civilizations that can simulate the universe. And I know this from my work in gamma rays, that I simulated far more gamma rays than I ever detected. And so possibly we're a simulation. So if we're going to use the multiverse to explain the designed, rare, unusual look of life here on Earth, then we're going to have to deal with all these other possibilities as well. And not only that, if I'm just an assembly of a particular set of atoms in a particular way, there's going to be another Jeff Zweerink out there somewhere. And there's going to be another day where we're having the webinar, and one where I just decide I'm not going to talk anymore and shut it and go home. If that's true, what does it mean for identity or free will and justice? And again, this is getting a little bit out of the science, but these are things that as people we hold very strongly to the idea that I have an identity, that I have a capacity to choose, and that justice is important. These things are important to us, but in a multiverse, they have no real meaning to them, or it's very ambiguous what they mean, if they have any meaning at all. And again, and I think it also impacts even what does it mean to do science? Because very often when we're doing science, we're not saying this is the only possible outcome. Really what we're saying is that this is the best explanation, or the most likely explanation. Well, again, in a multiverse, if we're using the multiverse to explain how all this information got in DNA and how life arose and all of that, well, then the unusual, unlikely, rare things are happening all the time. And so,
and of course, in one of those universes, Richard Dawkins is the Pope, and Sam Harris.
It does have to be possible, it does have to be possible. So.
Yes, Richard Dawkins is the Pope, and Sam Harris is a mega church pastor in some big churches in America.
So what are we doing when we're doing science if everything happens? Some have said, well, we can talk about things in terms of probabilities, but the reality of it is, in a multiverse, everything happens an infinite number of times. And so it really is unclear that we have any role for science if we're going to use the multiverse to solve the design that we see in the universe.
Now there are some recent data that we're getting that we need to analyze. The Planck satellite measures the cosmic microwave background radiation, and a few years ago there was a significant amount of new data that came out that allowed us to evaluate certain multiverse theories, etc. And this guy, the gentleman seen at the top right there, Paul Steinhardt, he makes some pretty good arguments that we have some reason from this data that would mitigate against the multiverse, and in particular the leading multiverse theory of eternal inflation. And he's got much more to say about this. So this is one provocative statement. Just so you know, Steinhardt is not some lightweight. He's the director of the Princeton Center for Theoretical Physics. He's the Einstein Professor in Science. So he's kind of in that chair now. He's got one of the cooler titles around there. But he says in a multiverse, each measured cosmological parameter represents an independent test of the multiverse. In the sense, one could expect large deviations from any one of the naive predictions. The more observables one tests, the greater the chance of many deviations from the naive predictions. Hence, it is surprising that the Planck 2013 data, that's the data 3 years ago from this Planck satellite, that it agrees so precisely with the naive predictions derived by totally ignoring the multiverse and assuming purely uniform slow roll down the potential. In other words, he's looking at a version of inflation that wouldn't necessarily entail the multiverse and saying, well, this explains the data. We don't need to, and in fact, he says it's surprising if there was a multiverse version of this that you would have the measurements that we actually had. because these kind of multiverse scenarios, this chaotic inflation, ends up producing wildly varying things. And so why do we get this simple version of things that is exactly what you would predict with a much simpler non-multiverse model? So another challenge to the multiverse as an explanation of fine-tuning would be that the theory should predict life-permitting universes, which would not be too dissimilar from our universe. And so that's where Penrose's critique that we've discussed already comes into play. But there are other things as well. One way to think about this, to see why this is important, would be to consider, again, the firing squad example. On the hypothesis that the firing squad was aiming at you, but they all missed, you would expect a pattern of bullets to maybe be pretty close to you, maybe right above your head or to your side. If you had enough firing squad members shooting at you, you might have a really nice outline of your body up there, because they probably, if they're true marksmen, they probably have a relatively small average aiming error, and therefore they're more likely to barely miss than to miss by a lot, and you can draw some conclusions from that. And this is the same kind of reasoning that's being attempted to be applied to the multiverse, as we're considering whether it's a good explanation for fine-tuning. And yeah, the jury's out on that, but there are a number of problems where it just doesn't even seem helpful at this point. There seem to be some parameters that are overly fine-tuned. And by that, you could say, well, it's not strictly necessary for life, but it's helpful, or it's helpful for certain aspects of life. Hawking points out the quark masses seem to be roughly optimized for the existence of the largest number of stable nuclei. We don't need all of those heavier elements for life to exist at all, but they certainly enrich our lives on Earth by all the different things that we can do using those available elements, and it probably helps life some as well, some of the heavier ones. Frank Wilczek has pointed out that proton lifetime is at least 10 orders of magnitude greater than is necessary for life. And so it's surprising, if there was a multiverse even, that we would end up having so few proton decays that we haven't yet detected one. Water, a lot more could be said about water, but that was one that was kind of recently we discovered how finely tuned that had to be for life. But all these special properties, they're probably not strictly necessary for life, but they sure help it a lot. We can keep lakes from freezing over with this ice forming at the top and then acting as an insulator. Moderation of temperature, both at the level of Earth and within an organism, are greatly helped by the high heat capacity of water. There's a maximal ability for water to cool organisms because of the latent heat of evaporation. Many more that could be said that are surprising, unusual properties of water that make it incredibly well suited for life. In terms of transport within cells and within the Earth, both. It's got some great properties for dissolving things, etc. Weathering, the way that ice freezes, since it expands, it breaks up rocks, it helps recycle nutrients. Water plays a very active role in protein folding. The water molecule gets involved in helping to establish the 3D shape. Morowitz, a biologist, says the proton conductance is almost unique to water. It's a key element in the biological energy transfer. So this most biofriendly compound just also happens to be very abundant. We would expect evolution to choose the most biofriendly compounds, but there's no way in which biological evolution could make water so biofriendly. And so it seems to be supportive of fine-tuning beyond what's strictly necessary, and therefore beyond what could be explained just by a brute force, throw a lot of universes out there, and eventually you're going to get one life permitting. Well, yeah, you'll eventually get one life permitting, but if it has other special features, I think Luke Barnes used the analogy that suppose a transportation device is what's being selected for or something. Yeah, you might have random ways of putting things together to form a car, and you might have a selection effect if you can only live if you drive in a car, say, or something. But I think I'm getting this a little bit wrong, but I think you'll see the main point will stand. But it would be very surprising, though, if that car had a built-in GPS capability, because that had nothing to do with its ability to transport you around. And in the same way, we seem to have some things that go beyond what's strictly necessary that seem to show a special biofriendliness to various fundamental aspects of physics and chemistry.
Okay, an anonymous viewer asks, always enjoy your talks, Luke. Do you know much about Robin Collins's work on the fine-tuning for the discoverability of the universe? It seems to sidestep the multiverse's strength in using a selection observer effect. What's your thoughts on it?
Yeah, it's an interesting case. I've read some of his stuff. So, I mean, well, I've met him a few times, and we tend to, if we've got something coming out, we send each other to read over each other's stuff. It's a bit more difficult to run the argument. So when I presented the cases I did before, it's just, can I ruin the universe? Can I just remove all complexity? And there's some easy ways to do that. The difference between can I discover this, can I discover that is a bit harder to do, but there are some interesting cases like that where I think it's pretty straightforward. So that's when he finally gets around to publishing this book, it'll be great. And to see how he puts that case forward. The way it avoids the multiverse problem is that the multiverse will explain, it'll give you observers, but it won't explain why those observers could do science. So you can't have a multiverse. You can have a multiverse explanation of why we see the conditions right for some sort of life form, but not for the sort of life form that could actually learn a lot of things about the universe.
What do you think about the argument put forward by Guillermo Gonzalez and Jay Richards in their book, The Privileged Planet? Are you familiar with that argument?
Roughly. I've only heard talks about it. I should get around to reading that book. As I understand it, the argument is that the bits in our universe where observers can live also happen to be very good bits for discovering how the way the universe works.
Right.
I'd have to look over in a bit more detail, but the cases I've seen are pretty interesting, right? The galactic habitable zone's a nice place to be. I'm not sure how watertight it is, but it's certainly interesting. It's worthy of a look. It's not the way it's usually characterized as we just get a nice planet somewhere.
Yeah.
But
they make the interesting point. They make a lot of it's basically a cumulative case, right? So not one example on its own is just interesting but not convincing, but lots of cases together then becomes a cumulative case. So one of the examples, for instance, is the sun is 400 times bigger than the moon, but also 400 times more distant, and so you get this overlap. So you get private solar eclipses, which in 1919 allowed us to confirm the predictions of Einstein's theory of general relativity, and so on. So our universe, so habitability correlates with measurability is the argument they put forward.
Yeah, perhaps. I'm just thinking about the Privileged Planet video. It seems that some of the main players in the public research really seem to be thinking along the same lines that we are.
Yeah, there's certainly some, there's some that recognize that it's far harder than most people think to have a life-permitting planet and so forth. The other thing about the Privileged Planet is their main thesis was more to do with wherever you find a life-permitting planet, it's going to be discoverable. And even they weren't, in some sense, arguing that there wouldn't necessarily not be a lot of life-permitting planets, but just that if there were, they would be in areas where you could also, or well-suited for scientific discovery. Yeah, I don't think they were saying it was the final word or anything like that, but it'll be interesting to see how this plays out as we learn more about other planets and suns and so forth.
Very good. Thank you very much for your presentation.
Thank you, Kevin. Nice to talk to you.
Alan, by the way, have you read Michael Denton's work where he talks about some other finely tuned things, such as his new book, for example, Firemaker, where he argues that our planet seems to be finally set up for discovering and utilization, manipulation of fire?
Yes, I have, and I think there is some force to that, and Robin Collins has done some good work as well on the fine-tuning for discoverability that I think those are more quantifiable too, by the way, than necessarily knowing the probability of a life-permitting planet across our vast universe. I think that's challenging to really bound that in a way that you can make a real compelling argument. So I think it's probably more promising that those kind of arguments where you can show that, hey, if the fine structure constant was just a little bit different, we wouldn't have been able to forge metals and have fire and all that. So Yeah, I think those are worth considering as well. And you fold them into a cumulative case argument, it just makes this all the more probable. You got to have, there's some additional baggage there, and that's where Occam's razor can come into play. I agree with physicists that would say the concept of the multiverse itself should not be argued against on the basis of Occam's razor, because it might be just a simple outworking of some fundamental laws. But as an explanation for fine-tuning, as I tried to show at least, there seems to be that you have to conjoin numerous hypotheses together before it's an adequate explanation. And that does come into play, at least in some minor way, with Occam's razor, which is just a heuristic anyway. But it points to, you've got to overcome several hurdles before it's an adequate explanation.
One of the reasons why this whole topic is kind of interesting to a lot of people, especially a lot of the audience, I presume, is because it does suggest a fine-tuner. And I think it gives a very good way of thinking about the fine-tuner and its relationship to the laws of physics. So let me run through this. I like to imagine a chessboard with chess pieces on it who are trying to work out the rules of chess. Okay, so all of these animate little chess pieces, they're watching other chess pieces move around. So they work out that it's a law of nature that bishops move diagonally. And if they keep watching for even longer, they'll work out castling. And finally, one day, one of them might pull it all together and actually write down the rules of chess. So all of the moves they see in the universe, all of those natural events, will be explained by those ultimate laws of physics, right? They have the rules. They know why everyone moves in that way rather than some other way. But suppose they then ask a sort of higher order question. They ask, why is it that we're not playing checkers? Why these particular laws? Now, you can read the rules of chess all you like. You'll never get an answer to the question, why aren't we playing checkers? It's just a higher order question. So if they wanted an answer to that, they would need to look beyond those laws. Okay, so I think we can put ourselves in a similar kind of situation. There is some way that the physical world is. Right? Now, when we think about writing down that way, if you're a theoretical physicist, what we imagine is that at some point in the distant future, at a meeting of the really important physicist society, Einstein's great granddaughter, Alberta, walks up to the blackboard and writes down some equations, and then physics is over. Okay, we've actually worked out the rules to our universe. There's some comedian who joked at this stage that what he'd love to see happen is that all of our reality dissolves and a sign comes up that just says level 2. But that idea of just that we've finished it, we're done. Like if you can imagine a chess piece reading the rules of chess, right? It would be us looking at that blackboard, just staring at that blackboard for a while and thinking, okay, now what do we do? All the natural events that happen around us would, why do electrons happen that way? All of that would be on the board. We still might have a question as to why that board rather than all the other boards. Because what you could do with Alberta's room is you could take the room that she's in, that little blackboard, and you could take the whole rest of the room and every other room in the place, and you could fill it with all the mathematical ways that the universe could have been, but isn't. Right? You have all of mathematics at your disposal. You can just grab a great big mathematics textbook. Right, this is handy. A course in modern mathematical physics. You can just pick any of these equations and write them down, and that's a possible way the universe could have been. Whatever ends up on Alberta's blackboard is one way. It's always going to be a particular way the universe could have been. And there will be all these other possibilities. So if you want to say why this universe rather than all the other ones, you'll still have that impression when you're staring at the ultimate laws of nature, even if we could write them all down on a board. So one of the things I want to suggest is that a good explanation doesn't leave you at the mercy of a huge set of possibilities if it doesn't have to. Okay, so here's an example of that, which I quite like. So if you remember the game Guess Who, So the point of this game, if you haven't seen it, is those are all the possibilities. Okay, so there's a set of cards, and you pick a card, and your opponent picks a card, and you have to try and ask questions about that card, their card, to try and isolate who it is. So you might ask, do they have yellow hair? And if they say yes, then you flip down all the ones who don't have yellow hair, which leaves you with that, you know, Joe is there and David and those ones on the back row. Okay, so it's about, so a good question, a good theory, if you like, is one that flips down a whole heap of possibilities. Right? So a good bit of evidence in a murder trial is one that takes a huge set of possible suspects and really nails down one particular person. That's why DNA is so important, because it's unique, right? Unless you've got an identical twin, if you know the DNA of the murderer, you've got one particular person. Whereas if your witness says they had black hair, but that's all I know, well, that still leaves a whole heap of set of possibilities, right? So what we want a really good explanation to do is to take a set of possibilities, like the set here, and flip down a whole heap of them, leaving open the one that actually exists. That's really what you want. So, for example, in Guess Who, if you ask, does your person have both a beard and a mustache, and they say yes, then it's Richard right there on the front row, okay? Because he's the only one who's got that. So those sorts of things which really nail down a small set of subset of possibilities and flip down a whole heap of other possibilities, those are good explanations. So let's go back to Alberta's blackboard, which is some particular way that the universe is. It's always going to be particular. There's always going to be, we could just take Alberta's blackboard and zoom out and put a whole heap of other possibilities there. The best thing we can do to sort of investigate those possibilities using the laws we know is to take those laws and change the parameters. That gives us a systematic way of working through all these other possible blackboards. So consider one little section here, and suppose it represents each blackboard represents one way that the cosmological constant could be. If you're a naturalist, if you think that matter and energy is the only stuff, then you're still at the mercy of all these possibilities, because there is no deeper reason why the universe is the way it is. You get to that blackboard, all explanations stop, end of story, right? You don't know why it is this particular one. So if we're thinking about the set of possibilities for the cosmological constant, is there a better way, is there a theory, an idea, hypothesis, whatever, which could help us nail down a smaller subset? And so if you believe that the universe is the creation of a good creator, for example, if you think that God would choose which possibility to create on the basis of which instantiates some good state of affairs, then of all these possibilities, you've now got a very small subset, which you would expect. So of all the values of the cosmological constant, most of them don't create any life form that could experience love, for example. So if you think that that's a valuable thing, if people are valuable, if loving, being loved, experiencing love, learning, having moral courage, all of that stuff is valuable, now you have a reason why, when you find out that there is a small value and not a huge value of the cosmological constant, why it is that way rather than all these other ways. That, I would suggest, is a property of a good explanation. So that, I think, is how this argument works. We've got a huge set of possibilities. If you're a naturalist, you're staring at a massive set of ways the universe could have been with no reason to go further. What I think fine-tuning shows is that if moral goodness is valuable, then we can get a step further in understanding why our universe is the way that it is. Now, obviously, Geraint disagrees, but if you want to see that play out, then the book's available on Amazon and Book Depository and in Kindle form and all of that sort of stuff. So go and Google it. And I think I can finish there. So thank you for everyone who stayed with it.
There's other things that could be brought in play to distinguish between a multiverse and God. You could argue that a designer would be more expected to favor intelligence The ability of humans to discover scientific truths would seem to be rare among evolutionary possibilities. It's surprising that we can understand quantum mechanics and general relativity given enough study. Thomas Nagel makes some of these points. Consciousness, you could have evolution and natural selection work quite well without ever having conscious beings. Even if you assume that eventually we'll discover a physical mechanism for consciousness, which I think is what atheism is committed to, or at least naturalism would be anyway, the illusory nature of these emergent properties would point to their being very rare. In other words, it's really hard to know how do you mix together chemicals and make them self-aware. It's got to be a very rare phenomenon. And so that in itself could point to an additional kind of fine-tuning that you would expect on theism, but would be surprising on atheism. Things like the perception of free will, objective morality might also contribute to that. All right, but what about some other common objections? This is giving up on science. And here I think Barnes has a good way of saying this, that positing God as a cosmic designer is not replacing a scientific explanation, but adding a personal explanation. And then I added this other part here saying, if you think about Aristotle's different way, there's different kinds of explanations that can be offered for things. And really the proposal that God set up the laws of physics, it's not competing with science. You're still, let science go, finish, do its work. There's good reasons for thinking even when science is done, you end up with these fundamental parameters that would be finely tuned. And therefore it still could support the argument for God. It could be evidence for God. And it would be no more giving up on science than adding a personal explanation to why the water is boiling. You could describe the chemistry of water boiling or just the physical aspects of phase changes, but it might not be the full explanation. That's the question. Is there an additional explanation? Science in principle wouldn't have an explanation for the most fundamental laws, constants, and initial conditions. There's nothing that would drive them to a particular value once you get to that most fundamental level. All right, it's also sometimes said that, well, this is just another God of the gaps argument. But I would argue that there's really no gap here. This is based on knowledge, not ignorance. It's certainly true that science will always progress, we'll learn new things, but all we can do is evaluate based on what we know now. And everything we know now about the foundations of science leaves us with a series of startling coincidences. A fundamental constant is defined as not being derived from a theory. What we're dealing with here is at the most fundamental level. If it is truly fundamental, then science is done. Now, sure, there might be some theories out there that make these not fundamental, but it seems very implausible to think that, and this is where some of those quotes by Wilczek and others, Rees, come into play, to think that there would be no coincidences once you have a final theory of everything. And really the thing to think about too is this uncertainty relates to high energy physics. That's where we don't really understand things very well, admittedly, but fine tuning is very dependent on low energy physics. There's simply too many cases of fine tuning to think this evidence will go away. And just to give you one example of someone that was impacted by this data, Frank Tipler. He was one of the original authors of this very important book that came out in the 80s by Baron Tipler, Anthropic Cosmological Principle. And he says this provocative quote, "When I began my career as a cosmologist some 20 years ago, I was a convinced atheist. I never in my wildest dreams imagined that one day I would be writing a book purporting to show that the central claims of Judeo-Christian theology are in fact true. I've been forced into these conclusions by the inexorable logic of my own special branch of physics." Now, I think he might be reading too much theology into physics, but I think the fact is that he saw this as evidence for God, and it had a really big impact on his life. And he wasn't really looking for it or expecting it. And so I think that's worth noting.
Big D asks, is the fine-tuning argument a form of God of the gaps argument? And if so, does it diminish the value of this argument?
I don't think it is. Certainly not in a way that many other God of the gaps arguments work. So if you want to say there's this specific thing in the universe, whatever it is, and natural things will not make this thing, and so that's a sort of gap in our scientific knowledge, or even if you want to say it's stronger than that, it's a gap in the abilities of natural laws as we know them. And so we need to explain this thing. I think fine tuning works differently to that. It's let's have science do everything it wants to do, right? Alberta's blackboard is the dream, right? You solve it. We have this is wonderful quote that the reason why physicists do is Ed Hines. The reason why physicists do what they do is because nature is the biggest, baddest crossword puzzle you've ever seen, right? Think of solving that. What next? Let science do all it wants to do, right? It's not that here's this thing and science can't explain that. No, let's get that final board and stare at it and think whether, when science has done all that it can do, when all of the gaps in that are full, and we can assume that they're all full, right? And this argument still works. Are we done? Have we reached the sort of explanation that we should be satisfied with? I think regardless of what goes up on the chalkboard, on Alberta's chalkboard, there's still a whole heap of questions. It'll still be a particular thing. There'll be a huge set of possibilities, and that property of that a good explanation flips down a whole heap of possibilities, doesn't leave you at the mercy of all those possibilities, is something that naturalism does when you get to the end of science. So I don't see it as a God of the gaps argument, certainly not in that sort of relevant way. We're not trying to say here's something science can't understand. We're saying let's do science, let's do all of it, let's get to the end. We're still going to have all these sorts of puzzles.
All right. Other people would say, well, there's kind of life chauvinism involved in the fine tuning. Why focus on life? The universe could be said to be finely tuned for black holes or rocks. Here's one skeptic's way of putting it. But one interesting thing about this claim is recall that the Penrose fine-tuning data shows that actually there was a great deal of fine-tuning that seemed to be necessary to prevent, or to minimize rather, the number of black holes in the universe. So it's actually seems to be optimized at minimization of black holes, and that does seem to be a natural consequence from most initial conditions would have been more black holes. All right, so I don't think people, the physicists writing these 200 peer-reviewed articles, they're not necessarily assuming that life would have to be carbon-based or human-like. I don't think there's necessarily this strong bias towards what life would have to be like. And one thing I might point out here too is that on theism, it doesn't seem very surprising that God would want at least some intelligent life that could know about him, that could interact with him. But on atheism, there's nothing that would there's no mechanism for setting fundamental constants that would somehow bias them towards their future effect on producing life or sustaining life. And when you look at how skeptics argue against God, they frequently will raise the problem of evil, which is a very significant challenge, I'll admit, although I think there's good responses. But yeah, if you raise the problem of evil, you're presupposing, though, that God would favor life, I think. So I think you can see from the way skeptics argue against God that the inference that God would want life somewhere in the universe seems to be fit quite well with that.
What do you think about the objection that's put forward by Neil deGrasse Tyson and others that we can't live in most of the universe, and so the universe really isn't fine-tuned except for this very localized spot?
So I think they misunderstand what fine-tuning is supposed to mean. It's not that this universe is, so P.Z. Myers said, why isn't the universe just a couple of light years of lakefront property with great fishing, right? It's not that this universe is the perfect habitat for us. The whole thing is, right? The idea is that this is a universe in which moral agents can live, and they're not just God's pets. They don't just have it all laid out before them. It takes moral courage to be morally good. You don't. It's neither impossible nor totally trivial to be good in this universe. You have to have some gumption about you. So I think that's just a misunderstanding of what we mean by fine-tune. What we really mean when a physicist says it is this the way the universe is versus all the other possibilities. right? Not the way that our bit of the universe is versus all the other bits of the universe we see around us. Now, the way deGrasse Tyson likes to say this is that most of the universe will kill you. That, you know, we've discovered that if you went out into the universe, you'd die in a fraction of a second. Now, the interesting thing about that is we had to discover it. It makes no difference at all to our everyday life. The vacuum of space, as far as I can tell, in the history of humanity, has killed 3 people. There were 3 Russian cosmonauts in the 70s who had a malfunction on re-entry, and all the oxygen escaped, and they ended up dead. That's it, right? If the universe is trying to kill us, it's doing a really terrible job. It's the worst assassin you've ever seen, right? We're you know, thanks to gravity, we're stuck down here with the atmosphere, and we just it's literally like I can't walk into the next room and experience the vacuum of space. I'd have to get, you know, 8 or 10 kilometers up for that to happen. So it's no part of this idea that humans are the sole purpose of the universe. The example I like to give for this is I can understand that the CD player in my car is designed, and I know why it's there, without having to assume that the whole car exists just to play music. And it's no objection to say, why doesn't more of the car play music? So why doesn't more of the universe permit life? Well, how much do you want to permit life? I mean, there's interesting little things, like if you filled the entire solar system with breathable air, the Earth, thanks to air drag, would spiral into the sun in about a couple of months. So look, there's a reason for the way the things there are. It's not we're not the sole purpose of the universe on Christianity.
Sure. So I think the way that I would argue that case is to argue that, okay, so it's assuming certain things about God and about theology, and on Christian theology at least, there's no reason why God would want to populate the entire universe with intelligent creatures. Yeah. And in any case, one could argue that the initial mass density of our universe is finely tuned, which would mean that the universe has to be as big as it is. And since God doesn't want to populate the entire universe with creatures, it may as well be not conducive to life, right?
Yeah. I think the point, that's a good point. It's just, we need to see some sort of reason for the features the universe has, and we know why the vacuum is there. It plays its own role in making the universe habitable.
Right. And also, Psalm 19 says, the heavens declare the glory of God, the skies proclaim the work of his hands. So if the purpose of our universe primarily is to display and exhibit for us intelligent creatures the glory and majesty of our creator, then there's no reason why it needs to be conducive to life. It just needs to be awe-inspiring.
Yeah. Yes.
This is a very common objection that should be discussed. People will say, well, the universe doesn't look like it's fine-tuned for life. It's mostly inhospitable to life. I can't go visit the vacuum of space or these faraway places. It doesn't look like it was designed for life at all. But notice that this fine-tuning claim is not claiming that life could live in every square centimeter of space. I think what they're really getting into here sometimes are theological presuppositions. If they're arguing against design by saying the universe is inhospitable, I think the thinking is that this is not how God would have done it. But theists have pointed out there are some logical reasons why he might have. Now, I would agree that it's hard to play the mind of God here, but note it's the skeptic that has the burden of proof, I think, in showing that God couldn't have a reason for making it this way. And we can at least brainstorm and see some reasons why he might have. God might have wanted a huge universe to humble us or show his glory.
What do you think about the argument that some people make that God doesn't really need to fine-tune the universe for life because he can do what he wants? In fact, we know if we're Christian theists, we believe in angelic or spiritual beings who are not embodied, and so God doesn't need to fine-tune the universe in order to populate a world. What would you say to that?
The question is how much of a hit your probability takes. The question is, must God make a universe like this? But is there a reason for God to make a universe like this? Richard Swinburne's The Existence of God, I think, is quite good on this. So if you want beings who can interact with each other, right, which seems like the most basic precondition for moral beings who can, love and learn and interact and take responsibility, all that sort of stuff. There has to be the thing that I am and the thing that you are, and then some public space in between by which we can interact with each other. There's got to be a difference between my actions and the consequences of my actions and the consequences of my actions for you. That, whatever that middle thing is, we would just call the physical universe, whatever kind of being you are. So even if you think that there are angels, if they can interact with each other, there must be something that, it wouldn't be the physical universe as we're familiar with it. There would be some public sphere or whatever it is. I don't know. Ask a Thomist.
Sure.
In that case, one of the problems I have with this objection is that I think it misunderstands the relationship between what God is supposed to be and what the laws of nature are supposed to be. I think if you have a picture, actually, again, Sean Carroll, this is his picture. What the laws of nature are is just the patterns. There are just events that happen, and we put them into a pattern, and those patterns are the laws. If that's your view of what scientific laws are, this objection literally makes no sense, because what it's trying to say is that God could make the laws of nature one way and the universe behave in a different way. He could make laws that wouldn't create life and then make it behave in a different way that would create life. But if you have that view of the laws of nature, those aren't two different things. They're the same thing. The way the universe behaves just is the laws of nature. So there's no objection there. There aren't two things. There's only one thing. You can't say God could make it so that the laws of nature are one way and the way the universe behaves is another way. That's because the laws of nature just are the way the universe behaves. What you'd be saying is the laws of nature are one way and the laws of nature are another way. That's just a contradiction. If, on the other hand, you think that just a naive picture that what the laws of nature are just tell us what the stuff of our universe can and can't do. So there are certain substances, they have certain properties and certain liabilities. There are electrons, they can attract other charged particles and they are attracted by other charged particles. There's just stuff that does things, right? On its most basic level. The picture you then have is that God sets up the laws in a certain way and then goes, oh nuts, it's not going to make life, and then is just constantly overriding his own laws so that there can be people in there. Now, what's the likelihood that God would make that sort of universe? That just makes no sense to me. Like, why not just get it right in the first place? Surely a good creator would just sort this thing out to start with. So it also, in that universe, it would be totally baffling. It would be almost impossible. One of the things you need to have a moral interaction in a universe is that Swinburne makes the point. You have to know the difference between, if I put this combination of matter together, my environment, whatever that is, the physical universe, will it make a house or will it make a bomb? Right? I need to be able to do that if I'm going to decide whether I build houses for the homeless or bombs for the homeless. And those are two morally different things. If you had a universe where there was these laws, but they were totally being overridden every now and then, the universe would cease to be predictable. It would just be totally baffling how things work. So that objection doesn't make a lot of sense to me. I don't see how. I mean, God would have thought through the environment he wants his creatures to experience, and then if we investigate that environment, we'll understand that it works via certain laws, and that all fits together for me.
And the problem of evil, which presupposes that God would care about life. So I think you've got some good reasons for thinking that on theism, God would favor life, would favor fine-tuning.
It's if you look at the scientific revolution, who is saying we need to go and look really hard at nature and we work out the laws that are underneath? Why do they believe there were laws? Because they were Christians and they thought that a good God made it, a God who is intelligent in some sense or another, put these laws, discoverable, rational laws in there. That's why they went and looked at it. And it wasn't totally clear what those laws were going to be when they started. Like Roger Bacon was one of the early advocates of this before Newton, before Descartes. He died shoving shoving snow inside of a chicken to see whether it would help preserve the chicken. He got caught pneumonia. When you don't know what the laws of nature are, you don't know where to look. And so you have this very haphazard view of things. The reason why they kept looking and paved the way for Newton and everything that followed was because they thought that God had made the universe. So I think that there is something there that the naturalist who just thinks that, of course, that there are these scientific laws that explain everything has really presumed something that his assumptions don't give him.
And so I think I've argued fairly well that for this concession that Millikan made, where he conceded that if there's an inexplicable coincidence in the fundamental constants of nature whose values have to be precisely tuned within a wide range of otherwise available possibilities that would make a complex universe possible, then this constitutes a phenomenon that very naturally invites explanation in terms of a cosmic scale designer. So I think the evidence from the fine-tuning does naturally invite explanation in terms of a cosmic scale designer. We could, there might be some debate about exactly how strong that is, but I think it's fairly strong because of these incredible levels of improbability. And you could point to other skeptics that would also seem to admit that fine-tuning is possible evidence of design purpose and creation and the choice of the laws.